let's go ahead and get started. I have some of these are not the right notes. So the nice thing about this class is you all have the same teacher. Here for 17C, can I see your symptom survey, please? Right, you are all in Rademacher's class, right? No other choice. So that makes things easy in that we don't have a lot of different professors who are doing different things at different times. We all get to be on the same page, which is going to make life better. And he's taught this class before. I think he does a pretty decent job of teaching it. So I think you're in relatively good hands with him. Not that you have a choice. I mean, I guess the choice could be to take the class a different quarter. But I imagine all of you would like to be done taking math, as for most of you, this is probably your last math class. Probably. I think everyone is here, so not that I'm not locking it. So now that you're all here, you should all mark your attendance. So there's QR codes. So I should point out before you scan them, the laminated ones that say, and you might be able to read it, might not. They say James's class attendance on them, not the other ones that are taped to the wall, but the ones that are on the chalkboard. Scan one of those, and it should take you to a Google form that you can fill out with your student ID number, your name, and I think a couple other things. When you enter your name, please write your first name first and your last name last. And try to write your name the way you think it appears in Canvas. For example, I have a student named Elizabeth, but on Canvas, her name shows up as Liz. And I do sort things alphabetically when I'm doing this. So you'll make my life easier if you get the first letter of your first name correct, which shouldn't be troubling for most of you, but some people do go by a shorter name that has a different first letter than their actual name. So please try and get that as accurate as you can. And if you get it wrong, it's fine. Just if you're not sure how it comes up in Canvas, you can always check later, and next time you'll do it whatever way is the right way. And it seems that that link is working for everybody, so good. It wasn't at the beginning because I accidentally had it linked to the version where you could edit it, and that was not excellent for the students to be able to edit my document. So I fixed it. It's good. If for some reason everyone should be able to scan the QR code from here in the room. I tested it out. I was able to do it from anywhere. But if you can't, there's also a link to the form in Canvas, so you can find it there. You can also just bookmark the page. And I suppose that should get to the point of talking about welcome. Let me see your symptom survey. And then after that, you should scan one of the QR codes, not this one of the laminated ones, to mark your attendance. And it'll probably happen that some of you might not do it right, or I might miss you. If you didn't do it, I'm going to mark you absent, and then you'll see it and be like, James, I was there. I filled out the form. I'm like, oh, great. Let me fix it. So if you get marked absent, you were here, just let me know. Can I see your symptom survey, please? Miss? So yeah, if you accidentally get marked absent, it's not a big deal. Just let me know. And the cat scratched my finger, like just barely caught my finger the other day. It's like this skin really thinking of something. Oh yeah, why am I taking attendance? Because that's how you pass this class. You just have to show up. You literally don't have. I mean, you should also participate and pay attention. If you're sleeping through class, I might say something to you. I might not. People need to sleep. I get it. I can actually take a nap right now, personally. But there was a point I had. Oh yeah, you're going to pass the class by being here. So that's why I'm taking attendance, so that you can track it easier and then give you an appropriate pass or no pass. Class is worth one workload unit, which means I mean, you guys are. I would imagine. Well, I guess I don't think anyone's a first-year student here, right? Like everyone's probably taken 17A and 17B at this institution. So not that you couldn't be a first-year student. If you are, that's totally fine as well. But my point was, you kind of all know the deal already. Probably all our students that we did this already. This is not your first rodeo. So you know the deal. Workload class, one workload unit, doesn't count towards graduation, does count towards being a full-time student. If you didn't pass it, it wouldn't be the end of the world, but I imagine all of you are going to pass it because that's based on attendance. What else do I want to say? There are optional quizzes because your whole grade is based on attendance. The quiz is totally optional. Like you can do it if you want, you do not have to do it. The point of doing it would be to get feedback on how well you're understanding the material. So if you take the quiz, which I think they're due every Monday, but they're really you can do them anytime. But I tried to write them so that they follow the course material in a timely manner. So the quiz for the first week should correspond to the material for the first week. Thank you. And so on and so on. If you take them, I will grade them and give you feedback. Be like, great, you got everything right, or oh, you made this kind of mistake here. And I try to give pretty detailed feedback in grade scope. So if you do one of the quizzes in grade scope, you should definitely look at the remarks. Even if you didn't miss any points, you might have, I mean, points, right? Because they don't have anything, but you might have still, there might still be comments there, me saying like, oh, you did this, you did this right, but there's this thing you might want to look at. So just, you should look at the comments if you decide to do the quizzes, which are totally optional, but highly encourage you to do them. What else? Let's see. So we have the grades, not the grade scope. We have Canvas up here, not grade scope. And it's got all kinds of stuff. I really feel like you don't need to read maybe any of this. Like there's some information, it's useful. You can get a hold of me by my email. If you want me to do something, like if you want me to talk about something in class, the best way to make that happen is to let me know ahead of time. So like if you're like, James, we did this thing in class today on Monday, for example, or on Friday, and I would really love if we could talk about it on Tuesday. You can either let me know, the best way to let me know really is by starting a discussion in Canvas. So any of you can start a discussion and be like, hey, James, I would love it if we could talk about eigenvalues or eigenvectors or whatever. Or you have a very specific question, like we were given this, I don't know, this function, we were asked to find the level curve zones. How do we do that? Or what are, right? So it's a great place to do it here. And the nice thing about here is everyone else can see it. I know that might not feel great because they're like, I feel like I'm asking a dumb question and everyone else can see it. It's really, I mean, what I would like to say is get over it. It's really fine to ask questions that you might think are dumb because everyone's going to learn from them. So if you have questions and you want to ask them, I really, really, really encourage you to do it in the discussion. That said, if you really don't want to, you can also send me an email. But discussions are the better place to do it because then everybody gets the benefit from your probably great question, even if you think it's dumb. And the real other great benefit is I will respond typically. And depending on like, maybe it's a Friday afternoon and we're not going to see each other till Tuesday. And you might need help with something before that. I'll respond. And the cool thing about Canvas in general, actually, is that in Canvas, there's a really easy way for me to write things in nice mathematical type, whereas on my email, there really isn't. So I can write like nice integral symbols and do all the matrices and all sorts of stuff on a discussion in Canvas. It's going to look beautiful. You can be like, yeah, I'm so glad I asked in the discussion, not an email. Or you can send me an email, but it won't look as nice. What else? I feel like we should just get to the math, but I guess I should ask, do you guys have any questions? My favorite part, by the way. Excellent question. So let's take a look at the syllabus. Attendance, a passing rate is 75%, meaning you need to attend and participate in at least 75% of the class meetings. I think we meet something like 19 times this quarter. because right, there's 10 weeks and today, that's 21 meetings minus Thanksgiving and Veterans Day. So I believe that's 19 times. 75% of 19 is more than 15, I think. 15, well, let's see. I mean, 75% of 20 is 15. So 75% of 19 is less than 15, but not 14. So you have to come more than 14 times, which is 15. So I guess you can miss 4 classes. Just how the math works out on that, I think. I mean, we could get out a calculator and check for sure. You might, I guess I'm not 100% positive that we actually meet 19 times. I suppose I could go count them up and we could figure it out together, but I think we'll just stick with that. So 4 classes is probably the most you can miss. Really missing class probably shouldn't really happen, because even if you couldn't come to class physically, you could come on Zoom, and you could come on Zoom and literally not turn on your camera and sleep in your room, as far as I'm concerned. As long as you're here, that's fine. I mean, everyone can and should pass this class. It's not, there's nothing to it other than showing up. Now, of course, right, sleeping through class in your room, while it'll certainly earn you a passing grade, what's the point of doing that, right? Because I mean, you're obviously all here to get extra help with math sentences. So while you're certainly welcome to do whatever you want, I hope you will come and attend and pay attention and learn all the things. Good question. Other questions? This map. I know it's not a question, but like, yeah.
Goes off the textbook a lot?
That's a good question. I actually don't. I was asking my coworkers, like, do you guys remember last time Rademacher taught this class, like, if there was anything particularly good or bad about what he did? And none of us really could remember, like, either way, to be honest. I feel like he definitely like labels his lecture notes, or well, the things he says aren't really lecture notes because like they're not that great, and they are not super easy to read. Like his handwriting, I don't think my handwriting is very good, but I do think it's better than his. Not to like disparage his character or anything. I think he's a perfectly nice person, but some people, just myself included, don't have great penmanship. Yeah, but it seems like he definitely follows the chapters of the book. So I would imagine I should go back. I wonder if I can find his. I think I might have. Yeah, I'm gonna go look and see if I can find his old Canvas page if it's still accessible. Maybe see what I can see from there just to see. Yeah. There's someone I was looking for that. Other things. Brain. Sorry, my brain is like brain. Okay. We meet until 3. Where can you get more help? In case you're concerned, I have office hours Monday, Friday in here at 11, Tuesday, Thursday in here at 9, also virtually Tuesday, Wednesday at 3:30. That might change. There's also the drop-in room, which is open Monday through Thursday, 11 to 4, Friday, 11 to 1, Sunday, 3 to 7. You can also help each other. You should definitely, like, you're all in the same class. I encourage you to study together, to work together, to do things together. I would hope your professor also has encouraged you to do that. You can also make an individual, that's what I need to do. You can also make an individual appointment with me, but this link seems to not work. So I need to fix my Calendly links because they all seem wrong. Let me double check that. Yeah, it's this card. Yeah, I'll fix that, but you can make an appointment with me. My availability is limited because I'm pretty scheduled, but I think most days I'm available from like 1 to 1:30, maybe to 2. Well, obviously not on Tuesdays and Thursdays because I'm here from 1:30 to 2, but yeah. And there's another thing I'm going to add here, which is Grant's website, which I encourage. If you saw me over the summer for 17B or 17A, or if we've ever talked about anything mathematical with me, I probably said you should look at Grant's website because it is useful. So if you look there, there's Grant. He's a great guy. Here is his link to the 17C material. And there's lots of great stuff. The links do work. He fixed them all, which is great. So there's like intro to 3D graphing, domain range level curves, all kinds. Oh, what? It was working just a moment ago. Huh. Oh, I'm on the old book. That's why. New book. We want the new book. There we go. So here's some, great handouts that he has created. I think it would be worth all of your time to at least take a look at it and see. And if you look at it, you will notice that I definitely use his notes for inspiration. He has lots of great examples. So don't be surprised if you have looked at them and be like, oh, James is doing the same thing. It's perfectly fine. What else? Yeah. I'm gonna add a link to the bottom of the syllabus here. I will also probably put a link. Actually, I might already have a link in the modules section. Let's take a look. I don't, but I should. In fact, let's just do that right now. Might as well. Cool. So now it's on the very first module in Canvas. And the modules is definitely where you might find anything like of value, I would say. There's a link to the class notes, but there aren't any yet because we haven't written it yet. But I will definitely post all the notes there, right, in a Google Drive folder that this will automatically link to. So it should be, so if you want to see something that I wrote and you missed it, it's there. And then, oh yeah, I would encourage you all. So we're going to be doing some graphing of phase planes, direction fields. I think phase planes, not direction fields. And while this is fine, yeah. This is limited in scope. I feel like someone else, I feel like there's a better website somewhere, but what I will say is, back to the modules. If you can download P-Plane, I encourage you to do so. It is a very useful visualization tool for looking at phase planes, which is what we're going to be doing for not the whole course, but certainly a large part of the course. So if you have the time to download P-Plane, and you can find it lots of places. This is the place I've always downloaded it from. Specifically P-Plane, you shouldn't need D-Field, but P-Plane is what you want. And then what else in the modules? I feel like I might need to update. Is this link still the one I want? I feel like this might not be the one I want. No, this is not. I'm going to change that link because there's a better one. GeoGebra for real, the best. Yeah, that's the one I want. This is a pretty, no. I mean, sure, why not? There's some cool graphs there. Anyway, this is, you might be wanting to visualize some 3D graphs. And I would encourage you to, right, I'm not great at drawing in 3D. Some people are, congratulations, you're a good drawer. But I am definitely not. So I will try to show you things in 3 dimensions. I will probably use this. And I always forget, like, can I just delete you? Yeah. Because it's really nice. For example, one of my favorite graphs. Well, that's maybe not y equals. Let's try that again. There we go. Okay. You can zoom out. Maybe. I mean, it doesn't really change a whole lot when you zoom out. You can also rotate this thing around. Ooh, fun times. Okay. This is a saddle, in case you didn't know. It's kind of cool looking. It really, I mean, literally, it's called a saddle because it looks like a saddle, right? It's like goes one way this way and one way that way. It's actually something I am mildly capable of drawing. Parabola. I'm only really drawing this because like I can. I was like, let me show you one thing I can draw. That's all right. So here's a saddle. Ta-da. Anyway, but I mean, it's an interesting graph. It's got some interesting features. I always think about it not like a horse's saddle, although that is also an apt comparison. But like if you're hiking and you're like climbing a mountain and you're like, I'm going up the mountain, and then you can go over, or you can go up to like another peak valley. That's also called a saddle for obvious reasons. So I would encourage you all to check out geogebra.org/3D. That is there. And I will also make that a link in Canvas at a later date. Let me write myself another note. If there's anything else worth seeing in the modules. Got some handouts. Oh yeah, some probability stuff. That'll be at the end of the quarter. We're going to want to look at that. Exam prep material. I've got some short practice exams. Some old Zoom recordings from last year, from last spring, which might be worth watching if you've got nothing better to do. I kind of hope you have better things to do than watch my old videos, but they might be helpful. And they are labeled so that you can actually find what you're looking for if you wanted help with, like, say, optimization or linear systems of differential equations, for example. And then what else do we have here? Quizzes and solutions. So I guess I should I mean, you can look at the solutions and do the quiz. It seems kind of silly to look at the answers to a quiz that doesn't count for anything if you're trying to learn stuff. But if you really wanted to, you could. But yeah. All right, the quizzes don't count for any points. So you're just doing them to get feedback on how you're understanding the material. You don't have to do the quizzes, but you certainly can and should. I would request, I do request that you please all do quiz 0, because it's just a practicing grade scope and me getting to know you kind of quiz. So if you could all do that, I would appreciate it. It's not required. If you don't do it, I will have no ill will towards you, but I would appreciate it if you do it. Let's see. That's pretty much all the Canvas stuff, I think. Assignments, yeah, there's the quizzes, which again are not due. Discussions, announcements. I will probably, at least for the first week or two, probably make an announcement every class day about, remember to do your symptom survey and show it to me when you get to class. I would encourage you all to do it like first thing in the morning because you have to do it. So that's certainly what I've tried to get in the habit of doing. Like once I'm eating breakfast, usually I'm like, oh yeah, I should do my symptom survey. So good times. Reminds me, I have a COVID test today because it's been almost 2 weeks since I had my last one. So I would also encourage you to schedule your 2-week COVID tests slightly more frequently than every 2 weeks. So you're not like coming up against the deadline and maybe missing it somehow. So I do one every week just because it's easier to have it built into my weekly schedule as opposed to my bi-weekly schedule, but do whatever you need to do. I will keep track of your attendance here. Again, so your attendance goes to this document right here. And you can see, oh, look, there's lots of you have filled it out. Excellent. And then I will take all that information and mark it over. I don't know, guys, about things, but just so you know, I will mark your attendance on the attendance page, and then you can see that you have attended or not. So just for example, I think everyone's here, but I'm going to mark someone absent, and then it might show up for you later. So Stephanie is here. Let's pretend that you are not here. So, right, if you saw that and you're like, no, James, I was there, you can email me and let me know, and I will mark you present. Yeah. Cool. Oh, come on. All right, cool. I think that's all I've got to say logistics wise. Any questions? Any more questions? Yeah.
So in this class, do you like already have the material ready, or do we have to like show up and ask you questions?
So I have material ready. There are definitely about 10 different things I could probably talk about today because there's a lot of things to get ready for this. But if you have things, you definitely should not hesitate to let me know, because while I am certainly ready to talk about whatever I want to talk about, if there are specific things you would like to hear about, I'm more than happy to do that. And I probably already have material with respect to whatever you could ask me about for this class, because we have materials. So yes, you don't have to come with anything. If none of you had any questions, I could stand up here and talk at length, and you could listen at length. But I would love it if you did have things, suggestions, desires, wants as far as what you want to hear about, because I mean, we're all in the same class, so might as well have it too, right? It's definitely also easier that you're all in one class, because then, right, you all want to be hearing about hopefully the same thing, because you're all learning the same thing at the same time. So that'll make it a lot easier than say like 21A this quarter that has 7 different teachers, and some of them are doing really different things, which you wouldn't think would be possible with introductory calculus, but you would be wrong. Some people do some really, really strange things. Luckily, that's not the boat you're in. How many of you took 17B in summer session 2? A couple of you, okay. They definitely got a little hairy at the end there with those 3x3 matrices and stuff. So fortunately, we are done with that. I imagine, so you had a class yesterday. Did you talk about any math? Yeah. I imagine you talked about some, I mean, I guess I looked at his notes, but I don't even like talk about functions of several variables, maybe. Cool. Before we talk about that, so we're going to do some 3D stuff for a while. We're eventually going to work our way back around to talking about well, linear systems of differential equations. And the way we're going to solve those linear systems of differential equations is going to depend very greatly on our ability to find the eigenvalues and eigenvectors of a 2x2 matrix. So I know everyone should have done that near the end of 17B. I think it's worth revisiting just for a minute, even though I know we're not going to see it again until a few weeks from now. I really want you to take to heart, you need to be able to easily and efficiently find the eigenvalues and eigenvectors of a 2x2 matrix, which isn't that hard. Like, it's definitely way, way easier than a 3x3 matrix, which is, I don't want to say terrible, but it's kind of terrible. So actually, I didn't print out the notes that I wanted to for that. So let me go ahead and go to Grant's website here. I know he's got some good examples here. That's not the one I want. New book, not the old book. Let's see. Oh, actually, I want 17B because that's where I'm really going to find what I want. Let's see. I can just be smart. There we go. Cool. It might also be worth watching the video for this at some point if you have time to kill. Let me go ahead and grab some examples here. Cool. All right. 3, 6, -1, -4. You can use any 2x2 matrix, but if you haven't thought about it ahead of time, the 2x2 matrix you use might have terrible eigenvalues. So it's nice to have matrices that have nice eigenvalues. Let's go ahead and make this a little bigger. Well, let's get this. Let's do that. There we go. Let's do that. Cool. Move it over here. So let's talk about finding the eigenvalues and eigenvectors of this matrix. Yeah, I'm going to talk about an alternate way. So there's actually 2 perfectly legitimate ways of finding the eigenvalues and eigenvalues specifically of the matrix. And you almost always, with rare exceptions, start with the eigenvalues. So to find the eigenvalues, we're going to find the determinant of, let's call this matrix A minus lambda times the identity matrix. So that's going to be the determinant of the matrix 3 minus lambda, 6, -1, -4 minus lambda. And usually instead of writing parentheses and brackets, there is an alternate notation for a determinant, which just looks like kind of a matrix, except it's vertical lines instead of brackets. It's kind of like an absolute value, but not actually. So this is also written as this. So if they're just vertical like that, it means take the determinant. If they're brackets like that, it means you have a matrix. They look very similar, they're totally different. I know it's kind of dumb, but it is what it is. Fortunately, taking the determinant of the 2 by 2 matrix is a very easy process. You multiply the diagonals, so it's going to be 3 minus lambda times -4 minus lambda. You subtract, and then you multiply the off diagonals. That's it. There's your determinant. And we're going to set that equal to 0. So finding the eigenvalues. Find the eigenvalues. We're going to take the determinant of your matrix minus lambda times the identity and set it equal to 0. And let's see what we get here. So typically the way this works out is you get some quadratic that you can solve usually by factoring, but I will warn you, we are going to see eigenvalues that are imagined because there are results that correspond to that we need to observe. So when we get to whatever chapter 10.2, I think, we're going to start seeing imaginary as well as real eigenvalues. Yeah. Can I zoom in? That's an excellent question. Maybe. Whoa, that's a big zoom there. Good? Cool. Can I zoom out? Yes. Okay. I wish this was a little better fit. I feel like I saw another hand. No, okay. So let's see. If we multiply this out, and I'll try to write big. My writing, as I mentioned before, is not excellent, but I always try to say the things as well. So also, I'm going to post, I will, after class, like moments after class, I will scan these, upload them to Google Drive so you can always look at them later. And they'll probably be easier to read them later because it'll be easier to see them. Let's multiply this out. Let's see. I've got 3 times -4. I've got 3 times negative lambda. I've got negative lambda times -4. And I've got negative lambda times negative lambda. And plus 6 equals 0. Let's write this in a more standard way. So lambda squared plus 1 lambda minus 6 equal to 0. And that definitely factors as lambda plus 3 times lambda minus 2. So our eigenvalues are -3 and +2. I would like to point out there is an alternate way for finding the eigenvalues of a 2 by 2 matrix. Yeah, I can leave that there for a minute. Or the eigenvalues are equal to, and this is really just coming from the quadratic formula. It's going to be, actually, I should back up for a second. Tau is the trace of a matrix, which is just the sum of the diagonal elements. So in this particular case, this matrix, which was 3, 6, -1, -4, the trace would be equal to 3 plus -4, which is -1. And we often use delta for the determinant of the matrix. So for this matrix, the determinant is equal to 3 times -4 minus 6 times -1, which is -12 plus 6, which is -6. Notice that these values, the determinant is this number right here, and the trace is the opposite of the coefficient right there. So in your quadratic formula, your quote unquote B value would be -1. Oh, I'm sorry. Thank you. Please feel free to let me know if I'm off screen because it happens more often than it should. Right, our B value would be -1 in our, right, here's our lambda squared plus lambda minus 6 equal to 0. Right, there's your B, the coefficient there, which is 1. And your A value would equal 1. And your C value would equal -6. So using the quadratic formula, it would be -b plus or minus the square root of b squared minus 4ac all over 2a. Or using this notation here, it's going to be the trace, because the trace is your -b, plus or minus the square root of the trace squared minus 4 times delta all over 2. I know this might seem a little bit like, why are we doing this? It's because later on, when we are classifying the type of linear system of differential equations that we have, knowing what the trace and the determinant of the matrix are going to make it really easy to be like, oh, this system is a saddle, or this system is a, oh God, what's the word I'm looking for? A spiral. And depending on what the trace and the determinant are, we can tell if it's spiraling inward, spiraling outward, if it's all pointing inward, all pointing outward. So I know I'm saying things you're like, I don't know what he's talking about yet. It's okay. But I just want to show you this because although you don't have to do it this way, it is a nice thing to know about because it's going to make it easier to see what kinds of things you have later. So although this might feel like more work at the moment, I promise you it's going to make things nicer in the future. So for this particular matrix, the trace was -1, the determinant was -6, and our eigenvalues are going to be -1 plus or minus the square root of -1 squared minus 4 times the determinant all over 2, which is going to be -1 plus or minus, that's 1 plus 24, which is 25, and the square root of 25 is 5 over 2. -1 plus 5 is 4 over 2. And -1 minus 5 is -6 over 2, which are exactly the same values as we got doing it the other way. So I just want to point out, either way you do it, as long as you do it right, you should get the eigenvalues. There are two equally valid ways of getting them. I'm sorry, could you say that again? Oh, so I was looking at this polynomial here and saying this is like an a times lambda squared plus a b times lambda plus a c, where a is 1, b is 1, c is -6. But really, more generally, it's that the b value is the negative of the trace, and the c value is the determinant, and a is 1. That's what always happens in a 2x2 matrix when you write the characteristic polynomial, which is what this polynomial is called here. Or sorry, this polynomial here. So I would say don't worry too much about this. You should find eigenvalues whichever way you want. But I just want you to see this because we're definitely going to come back to it later. And it's a nice way of doing it. It's also nice because, so for example, later on, when we see, I don't remember, I think, yeah. If you look at a matrix and you, so for example, I can look at this matrix and just by looking at its determinant, since its determinant is negative, I know the phase plane for the system of linear differential equations that this matrix represents. I know that phase plane is a saddle. And you automatically get to know that because the determinant is negative, as opposed to seeing it's a saddle by doing a bit more work. So I know we're not there yet. I know I'm saying things that don't exactly make 100% sense yet. just trust me. It's gonna make sense, and doing it this way is gonna be nice for you. Question? No, okay. Either way, we've got the eigenvalues. Now let's find the eigenvectors. Because we do need the eigenvectors as well to write the solutions to the linear system. So again, our matrix is, where'd you go? 3, 6, -1, -4. And our eigenvalues are 2 and -3. And typically we label them as, like, one of them is lambda1 and one of them is lambda2. Usually the positive, if one's positive, one's negative, we usually make the positive one lambda1. They're both positive, usually the bigger one is lambda1. It doesn't really matter though. Here's how we find the eigenvalues. Eigenvectors. So if you remember, the eigenvectors are the solutions to this equation. A times the eigenvector equals lambda times the eigenvector. That's the whole idea, is that an eigenvector is a vector that when you multiply the matrix by the vector, it ends up just being a scalar multiple of the same vector. So we're trying to find a vector that meets this criteria. So our job here is we want to find the vector v. Okay, well, let's write it out a little bit more clearly. We have the matrix A. The vector v should be a two-dimensional vector, right? A vector with two components. We usually call them x and y. And it's going to equal lambda, which let's use lambda1, which is 2. So what should happen is this matrix times this vector should equal 2 times the same vector. And what we're going to do is look at the first equation. So this actually represents a system of two equations and two unknowns. The first equation is 3 times x plus 6 times y equals 2 times x. Right, that times that plus that times that equals that times that. And the second equation would be -1 times x plus -4 times y. I would probably just write -4y equals 2 times y. So here's the great thing about this. You don't need both those equations. You only need really the first one. Either one is fine. If we just use the first one and say solve for y, I'm not even really going to solve for y. I'm going to get 6y equal to 2x minus 3x is -x. And honestly, that's where I usually like to stop. I would then pick values. What's a nice number I could pick for x? Maybe a better question is, what's a nice number I could pick for y? How about 1? If y is 1, what does x have to be? -6. There's your eigenvector. Maybe you pick something different though. Maybe you would prefer to pick, this is not the choice I would make, but maybe you want to pick 1 for x. I would not make that choice, but that's fine. If we make that choice, then y has to equal -1/6. The point is, both of these are eigenvectors for the eigenvalue lambda equal to 2. And there's a lot more. Any multiple of that is also an eigenvector. So you can maybe pick something like, I don't know, 1200 and -200. That's also an eigenvector for this eigenvalue. Any non-zero multiple of an eigenvector is also an eigenvector for the matrix, for the eigenvalue. Typically, we try to make the choice where there aren't any fractions and where it's reduced as much as possible. So this is kind of the ideal choice of eigenvector. Or maybe 6 -1. That would also be ideal in my opinion. So really any choice is fine. And the point is that if you multiply this matrix times this vector, 3 times 6, 3, 6, -1, -4, times the vector -6, 1, 3 times -6 is -18, 6 times 1 is 6, -1 times -6 is 6, -4 times 1 is -4. We end up getting the vector -12, 2. which is exactly 2 times the vector we started with. That's the whole point. And then we can do the same thing for the other one. To find the eigenvector for lambda equal to 3, we do the same thing. 3, 6, -1, -4 times xy equals -3, not +3, times xy. And let's see what happens. We have 3x plus 6y equals -3x. Bring the x over, you get 6y equal to -6x. Some people do like to solve this for y. So like in the previous one, we could have solved and gotten y equal to -1/6 x. Here we could solve and get y equal to -x. The nice thing about solving for y is it does tell you what the eigenline is. So the line y equal to -x is the line that all the eigenvectors would go through. So any vector starting at the origin and terminating on this line would be an eigenvector. So there's an eigenvector. There's an eigenvector. There's an eigenvector. Right? Take your pick. Any of those would be an eigenvector. I'm going to make the quote unquote easy choice and pick x equal to 1, y equal to -1. Yep, I sure can. Also, just notation wise, if I'm calling this eigenvalue lambda 2, I'm typically calling this eigenvector v2. Similarly, for the previous one, I should have called the eigenvector. Sorry, and I'm getting just one sec. I should have called this v1. Great, we found the eigenvectors and we found the eigenvalues. That's it. So we need to be able to do that. And I don't think Rademacher gets too much into finding the eigenvectors for imaginary eigenvalues. It is something we might have to do. So this was a relatively nice example where the eigenvectors and eigenvalues were both nice integer numbers. They're not always nice. So we'll definitely see more of that later. I did want to do one more example. I'll just make something up because I know it'll work out fine. Let's look at another example. Let's look at the matrix. Sure, doesn't really matter. Let's go 6, 4, 0, -5. So there's a great thing about matrices like this or like this. Or like this. Any matrix where the lower left corner is 0 or the upper right corner is 0 or both of those are 0, you automatically get to know what the eigenvalues are. You automatically get to know what the eigenvalues are the diagonal elements. So for this matrix right here, the eigenvalues are 6 and -5. For right here, they are 1 and 2. Right here, they are -6 and -3. Kind of awesome. We can also find them the long way, but really all you're doing, you're saying, okay, if I want to do the determinant of b minus lambda I equal to 0, well, let's see. B minus lambda I is going to be 6 minus lambda, 4, 0, and -5 minus lambda. But when I do the determinant of that, the product of the diagonals is 6 minus lambda times -5 minus lambda, minus the product of the off diagonal. Since there's a 0 in one of those spots, that product is always going to be 0. And so you don't get anything there. And when you set that equal to 0, you've already got it factored. And the solutions are lambda equals 6 and lambda equals -5. So you'll see a lot of this happen, right? Professors, not every matrix is going to be up. So this is called an upper triangular matrix because everything at or above the diagonal is non-zero and everything below the diagonal is 0. This one is called lower triangular. And this one's called diagonal. Whenever you have an upper or a lower triangular matrix or a diagonal matrix, the eigenvalues are automatically diagonal. So professors use them a lot because it's just easier Like you will definitely see a question, you'll probably see a question that'll ask you to find the eigenvalues for matrices like this. And really the question will be like, for this matrix, classify the system of linear equations, like what kind of solution we have. And I can tell you, looking at that, we also have a saddle because one eigenvalue is positive and one eigenvalue is negative. Or looking at this one, we have what's called a source because both eigenvalues are positive. Here we have what's called a sink because both eigenvalues are negative. We'll learn more about that later. I know I'm saying words that might not really matter at all, but the point is, if you've got a matrix like this, it's easy to find the eigenvalues, and you should take advantage of them for sure. You should not write this. You can write it now, of course, but like in general, if you're asked this question, you should be not doing any of this. You're like, yeah, there they are. Done. The point I wanted to make about this really though was that finding the eigenvectors for this is a little strange. It's not super strange, but it's a little. It can feel a little misleading. So let's find the eigenvalues for that B one, or eigenvectors for B. Oh, and I should show you the other way of finding eigenvectors too. So we'll do one way and one the other way. I like to find the eigenvalues by solving. Sorry, I said eigenvectors. Holy smokes! I like to find the eigenvectors by solving this equation. So for lambda equal to 6, lambda 1 equal to 6, we're going to have 6, 4, 0, negative 5 times xy equal to 6 times xy. And if we look at the first equation here, we're going to get 6x plus 4y equal to 6x. What happens to x? So what do we get for y? We get 0. If y is 0, well, what about x? Did we still get the other equation? It can't hurt, right? Let's look at the other one. So the other one is going to be 0 times x minus 5 times y equals 6 times y. That's not great either. 0 equals 11y, y equals 0. Well, we already knew that. So if y equals 0, what does x have to be? That's actually the only thing x can't be 0. So, and I was hoping someone would say that. Thank you for saying the thing I wanted you to say, even though it's the wrong thing. Perfectly okay. It's great to be wrong because then we get to learn. 0, 0 is never an eigenvector. So if you're thinking about eigenvectors, you should always be like, it should never be the 0 vector. It actually has to have some length to it. So I will point out 0, 0 is a vector, but it's lame. It's just a point, right? It doesn't go anywhere. It's not worthless. It's actually a very important vector, but it doesn't have any magnitude or length. And an eigenvector has to have magnitude or length because the whole point of an eigenvector is that when you multiply the matrix by the eigenvector, it scales it. It makes it larger or smaller. And the 0 vector, technically, you could say it's getting scaled because anything times 0 is still 0, but it seems silly. So I just want to emphasize to you all, the 0 vector is never an eigenvector. So if y equals 0, it means x has to be anything but 0. And literally, anything but 0 is correct. So you could say, James, I'm going to say the eigenvector here is, I'll pick my favorite number, 8. 8, 0. That's a perfectly good choice for the eigenvector. It's not the best choice, but it's a perfectly legitimate choice. But what choice do you think I actually want to make, really? Right, I heard someone say it. 1, 0. So typically, if one of the entries for an eigenvector is 0, we automatically conclude that the other one's going to be 1. You can pick anything that's not 0, but 1 is the normal choice to make. It's the boring choice, but it's the choice that we're all going to make because it's just easy. Yeah, let's go and find the other eigenvector. I think I've got enough room to squeeze it in here. So let's see. Oh, I was going to do it the other way, which I don't really want to. Well, let me do it fine, I'll do it the other way. So when I say the other way, here's what I mean. Instead of trying to solve b times v equals to lambda times v, the other option you have is trying to solve b minus lambda times the identity times v equal to the 0 vector. That is your other choice for finding an eigenvector. Here's what that looks like. I don't prefer to do it this way, but that's okay. So let's actually do it, let's do it for lambda 2 equal to -5. So doing it this way would look like our matrix 6, 4, 0, -5 times our unknown eigenvector equal to -5 times our unknown eigenvector. Or we can do it this other way, where we take our matrix and we subtract lambda in each of the diagonals. So we're going to get 6 minus -5, or 0, and -5 minus -5 times the unknown eigenvector equal to the 0 vector. Both of these should give you the same result, or at least results that are equivalent to each other, not exactly the same. Doing it this way, the two we get. So I have 6 times x plus 4 times y equals -5 times x. Adding 6x to both sides, I get 4y equal to -11x. Here's a nice trick. I don't love solving for y. There are good reasons to solve for y, and I will. But here's a nice way to get the eigenvector once you have something times y equals something times x. The x coordinate is the coefficient of y, and the y coordinate is the coefficient of x. It totally works every time. Right? If x is 4 and y is -11, then 4 times -11 equals 4 times -11. Oh yeah, it totally works. That's the way I like to do it. You can also solve for y. Y equals -11/4 times x. And then you could pick x equal to 4 and get y equal to -11. Or you could pick the less nice choice, x equal to 1, and y is going to be -11/4. We typically try to avoid fractions if we can in our eigenvectors. It's not always avoidable. Sometimes you have to have a fraction. That might not actually be true. If your eigenvalues are irrational, meaning it has a root, or if they're imaginary, then it's hard to avoid unpleasantness. Or we could have done it this way. This boils down to 11, 4, 0, 0 times xy. 0, 0. So the first equation is 11x plus 4y equal to 0. And we're back over here, right? 4y equals -11x. So either way you want to do this is fine. My personal preference is to do it this way. I will say, though, this is actually worth mentioning. If our eigenvalues are nasty, like if we have imaginary eigenvalues or irrational eigenvalues, it is usually easier to find the eigenvectors doing it the second way. So I will just say that because it is true. It's just easier to do the math, right? Because if you have like a gross eigenvalue here or gross numbers here, then this times x plus this times y equal to this times x, and getting the x parts together gets a little messy. So I will just say, if your eigenvalues are nice, do it this what I think is the easier way. But if your eigenvalues are gross, what time is it? 2:40. Okay. The hard part about an hour and 20-minute class is like it feels like not quite long enough that we should take a bathroom break in the middle, but I kind of want to. But it's like now there's only 20 minutes left. It feels kind of silly to think, and not that I need to use the bathroom microphone, but use more water. Also, you're all welcome to drink beverages during class. I think you're actually forbidden from eating, but you are welcome to drink a beverage if you need to drink a beverage. So feel free to bring water or whatever you want to drink in future classes. Thought I saw a question. Okay. Do you have any questions about any of the eigenvalue, eigenvector stuff I've said? It's a mostly straightforward process to find eigenvalues and eigenvectors. I know that's not what you're doing in class right now. It's what you did in 17B whenever you took 17B. But just be aware it's coming back. So it's not hard to do, but it is worth spending a little bit of time practicing. So if you want to look in the book, I really don't remember what chapter this is in. I could find out. But if you want to go practice on some 2x2 matrices, finding the eigenvalues and eigenvectors, it's probably not a bad idea. It's definitely not a bad idea. Not probably, it's definitely not a bad idea. All right, 20 minutes. Let's go ahead and swing back around to what you guys are probably actually looking at, which is functions of multiple variables. Where do I want to go here? No, I don't want to do that. There's a lot of things to say about functions of multiple variables, but I feel like that's a good place to start. Sure. I like this pen. Let's talk about domain and range. Again, just a plug for letting me know what you want to see. I think this is important. I'm sure you'll cover it in class, but if there are other things that you want to see, you should let me know in the future. So maybe let's recall back to functions of one variable, something like, I don't know, f of x equal to the square root of x plus 4. The domain is the set of all possible x values. And for a function with the square root, we know that we can't. So when we talk about functions, there's kind of some implied language there that doesn't always get said. When I talk about a function, its domain is the set of all values that give you real number outputs. So even though we are going to be talking about imaginary numbers in the future, when we talk about the domain of this function, x has to be a value so that when you find f of x, you get a real non-imaginary output. So here, to find the domain, we're going to set the argument of the function x plus 4 to be greater than or equal to 0. Because we can't take the square root of a negative number and get a real output. And this one's very straightforward to solve. We get x greater than or equal to -4, which you could write that way, but most people are going to want you to write the domain of a function of one variable in the interval notation. -4 inclusive, the bracket, all the way up to infinity, exclusive, which always gets to parentheses because it's not a real number. Okay, well, we should talk about the range too. The range here is probably easiest to see just by graphing it. Square root of x plus 4 is the square root function shifted 4 to the left. Which also, I should point out, Desmos is also a great tool for graphing things in 2 dimensions. It's kind of cool. Like, I think Desmos is really nice for showing you how shifts and transformations work. So right, there's square root of x, and if I just add in a 4, oh yeah, it shifts a 4 to the left. And it's, I think, ooh, I didn't even think about this. Like a table, yeah. So cool. I would like more values on my table, please. Awesome, yeah. But you can kind of see how if I add 4 to x here inside the function, all the x values shifted 4 to the left, right? Before I had 0, 0, I should say I had 4, 2. And now when I add 4, I get 0, 2. And I had 9, 3 as a point, and now I have 5, 3. So my y values kind of stayed the same, and my x values all got to be 4 less. And the reason for that is because you're adding 4 to x before you take the square root. Oh yeah, the x values need to be 4 less to get the same resulting y values. So anyway, I mean, that's kind of neat. Yeah, I feel like I want to do something that was brain. I know, yeah, okay. So anyway, this function looks like this. And its range is just the set of all y values. which in this case is everything that is greater than or equal to 0. Or in interval notation, bracket 0. So that's all well and good for functions of one variable. But now we talk about functions of two variables, things get a little bit more complicated. So let's look at another example. I should have come back with the full beverage. I did not. Oh well, I'll make it. I mean, I can literally like walk out the door and get more water, but seems unnecessary. So let's go ahead and keep my notes in order here. Let's look at something like f of x comma y equal to the square root of 25 minus x squared minus y squared. So here, the domain is the set of all coordinates x, y in the plane that can be inputted into the function. Inputted into seems like maybe the same word twice. I feel like you just inputted. No, you feel like you didn't. So for example, I'm just going to name some points. 0, 0, definitely in the domain, right? You can plug in 0 for x and 0 for y. It's for 25 is fine. And 1, 4, totally in the domain. 25 minus 1 minus 16 still is going to be positive, and you take the square root of the positive number. It would be, let's see, if you plug that in, you would get what, the square root of 8, whatever that is, something. What is the square root of 8? Like 2.8-ish, I think. I only know that because I know the square root of 2 is like 1.4, and the square root of 8 is just 2 times the square root of 2. But then there are things that are not in the domain, right? The point like, I don't know, 6, 2 is not in the domain. Right? If you plug in 6 for x and 2 for y, you're going to get the square root of a negative number. So our job here is to figure out what's in the domain. And the way we're going to do that is the same kind of way we did before. We're going to set the insides of the square root to be greater than or equal to 0. I know what I wanted to say. Last class. I should point out odd roots, like the cube root, don't have any domain restrictions. So if someone said, just to back up a little bit, like what's the domain of f of x equal to the cube root of 2 minus x squared? You don't even have to think about it. Domain is everything, because you can always take the cube root of a positive or a negative number. The cube root of negative 8 is negative 2. The cube root of negative 7 is some terrible number that is negative 1 point something. But there is a cube root of negative 7. It's a real number. It's not imaginary. Odd roots are perfectly fine, because if you take a cube root of a negative number, you're asking what times what is equal to a negative number. And a negative times a negative times a negative is still negative. Works out great. Even roots, obviously, we have a problem, because a number times a number can't ever be negative. A real number times a real number can't be negative. This is a real number times the same real number can't be negative. Two real numbers totally can multiply to negative, just not if they're the same. So I really missed there being a clock in here. Clock would be great. In case this may, I just want to make sure everybody did fill out the attendance form. There's the QR code. If you didn't, I'll mark you absent, and then you can let me know you're here. So solving this, the problem with solving this is it's not as nice of a solution, right? Typically what we look for, and there are lots of things to look for, but if you have an x squared plus y squared, that's often something you want to try and isolate. So I would see this as 25 minus the quantity x squared plus y squared. And then I would add that to both sides. So I would have 25 is greater than or equal to x squared plus y squared. And honestly, I would really write it as x squared plus y squared less than or equal to 25. So when you have an inequality like this, what you want to do is kind of ignore the inequality part, meaning think of it as an equality instead of an inequality. So what kind of graph is x squared plus y squared equal to 25? Yeah, it's a circle. You guys are like, is he actually wanting us to answer, or is he just going to talk more? I very much, I got used to teaching last year, saying all the words all the time because students were not saying the words this time. But I will try to be better about letting you know when I want you to. You're always welcome to respond. I would like to hear your responses whenever you've got them, and I'll try and make it more clear if I'm specifically like. I'll probably do something like this, which is really cool, I know, but yeah, yes, I want your responses. So we know that x squared plus y squared equal to 25 is a circle. Center at the origin, radius 5. Looks about like that. We can label some points if we really need to. Okay, great. So if we want our domain to be where x squared plus y squared is less than or equal to 25, here's what's always going to happen. Whenever you have a domain in 2 dimensions like this, and you have some boundary, it's always going to be all the points on one of the sides of the boundary. So it's either going to be all the points inside the circle or all the points outside the circle. And we actually already tested some points. We know that 0, 0 is a satisfactory point. We can look at it again though, right? Is 0, 0 satisfying this inequality? For sure. 0 squared plus 0 squared is less than or equal to 25. So 0, 0 is the domain, which means that, I lose my red pen. I know I have it over here. There we go. Which means that all of the points inside and including the boundary, that's our domain. It's all the points inside and on the circle, x squared plus y squared equal to 25. There isn't really a much nicer way of writing this. The way people would probably typically write this domain is the set containing all the points x comma y such that x squared plus y squared is less than or equal to 25. It doesn't really get more descriptive than what we've gotten to, other than saying we know it's a circle and it's everything inside the circle. What else do I want to say about that? If the inequality was x squared plus y squared was strictly less than 25, your domain would be everything inside the circle, but not including the boundary. So for example, if your function instead was say like f of x comma y, if it was the natural log of 25 minus x squared minus y squared, then we would be setting 25 minus x squared minus y squared to be strictly greater than 0, because you can't take the log of 0, but you can take the square root of 0. Then our domain would end up looking like x squared plus y squared is strictly less than 25. And graphically, what we do is we draw the border dashed to indicate that it's not being included in the domain, if you're being asked to draw it at all. So here the domain would be everything inside the circle, but not including the circle itself. Oh man, I have to sneeze. It's gonna be terrible. Maybe not. I mean, it's kind of the worst when you have to sneeze and you don't. Like I kind of would prefer to sneeze here, but also not. Am I running out of paper? I ran out of paper. I guess I can use the back side, right? Paper's got 2 sides. So, I'm always worried I might go too far over. Let's talk about the range here. So we're still looking at f of xy equal to x squared, sorry, equal to the square root, oh boy, of 25 minus x squared minus y squared. And talking about the range. So the domain, we already figured out was everything inside the circle. I'm gonna try and draw this. Yeah, I can draw this all right. So here's our circle in like 2 dimensions. And we're going to add a 3rd dimension here. What this actually looks like is the top half of this sphere. So this, my pictures are, this is where GeoGebra would be excellent to use. You guys can kind of see it, I think, maybe. You guys like, no. Here's the circle. It's the domain of this function. And then this top part here is actually the function values. So for example, this point here, whoops, okay, yeah, maybe I can see why you're like, James, your picture sucks. That point there is kind of supposed to be the top, which is supposed to be over like the origin, which I know I didn't do a great job of drawing. That point there would be 0, 0, 5. All right, if x and y are both 0, the z value is 5. I feel like there's something in my eye. Sorry. And just looking at this picture, well, maybe looking at this picture, you can see that the range, the lowest the z values could be are 0, because you can't take a square root and get out a negative. And the highest the z values can be are going to be 5. Typically, the way people kind of go about doing this, if you don't see the graph or have the graph or know what the graph looks like, is you kind of think about what's going on with x squared plus y squared. So we already know that this has to be greater than or equal to 0. But we also know that x squared plus y squared itself has to be greater than or equal to 0. Right, that's just true. X squared, positive, is non-negative. Y squared, non-negative. Add them together, still non-negative. And we also have this. So typically what people do is they kind of, if you have an x squared plus y squared, which you won't always have, but if you do, they kind of hone in on that and then manipulate it. So I want this to look like that. So I'm going to take the negative of everything. When you multiply by a negative, change the direction of the inequality. I know negative 0 seems like a silly thing to write, but so I multiply everything by negative 1, and I'm going to add 25 to everything. So it looks like 25 minus x squared minus y squared is not surprisingly bigger than or equal to 0, because it has to be, because that's the domain, and it's less than or equal to 25, because the biggest this can be is 25 when x and y are both 0. And then we can take the square root of both sides, or all sides, and say, okay, our function f of xy is between 0 and 5. That's one way of getting at the range. Now, not every function has a nice range like this. This one happens to. There's something else I wanted to say about that. Not really, maybe. I wish my picture. So I will say, we'll say it's 3 o'clock. So we're done, but you can look at this in GeoGebra, which might be worth your while. No. I really think I need to sneeze. But if you want to look at this in GeoGebra, you totally can. And it's kind of cool. Oops. When you use the powers, you have to make sure to get out of the powers. Otherwise, things get really wacky. So there you go. There's your nice looking hemisphere, top half of sphere of radius 5.